So where we have to determine the derivative of f of x, which is equals to 1 minus x all divided by x plus 2 from first principle. So we're doing first principle. It's not visible in the question paper here. So from first principle, we know that the derivative of the function equals to when we limit the function h approaches 0. Where there's x, we're going to substitute what we call x plus h. Then all divided by this x plus h in brackets, then plus 2. Then the rule says that we need to subtract what? We need to subtract f of x, isn't it? So when you subtract f of x is there, which is 1 minus x all divided by x plus 2. Then the formula says that we need to divide by h. So we need to divide by h. Then from here we know we have to add fractions. So we're going to say limit h approaches 0. We're going to add fractions in the numerator there. So adding additions of these fractions, we know that the simplest way we said we're going to multiply the 2 and cross multiply the denominators with the numerator. So we're going to say x plus h plus 2 multiplied by x plus 2, isn't it? And then from there, we're going to say this denominator multiplies that numerator, which is 1 minus x multiplied inside the bracket minus h multiplied by x plus 2. Therefore, minus this numerator, I hope you see, it is in bracket 1 minus x, it is multiplied by the denominator there, which is going to be x plus h plus 2. Then, because of space there, let me just do the double division here. But normally I said write the division on the side so that can change the division sign to multiplication sign and have the h in the denominator. Therefore, the solution is going to be equals to limit h approaches 0. So let us multiply out now. So we see that we have 1 times x, which is going to be x 1 times 2. That is 2, isn't it? Then we move to negative x. Negative x multiplied by x minus x squared. So minus x multiplied by 2. So minus 2x. And let's move to a negative h multiplied by x. Negative xh. So negative h multiplied by 2 is negative 2h. Then go and multiply now the last term. So this is how we've done it yesterday. So we see this negative sign influences, can say either above brackets. So this one is going to be positive, while one is going to be negative. While one is going to be negative. So therefore, we'll say negative 1 multiplied by x is going to be negative x. So negative 1 by h is negative h. And negative 1 by 2 is negative 2. So I don't have enough space here. And we're going to say now, let me just add more pages here. So we're going to multiply now our positive x there. So as we said, let me just rewrite it here. And we have negative. This is positive x. So moving on to so it's positive x times x is going to be x squared, and then positive x times h plus x h, and therefore then positive x times 2 is 2x. Then I think we have all the terms that we're supposed to have. Xh plus 2, it's 5, and all divided by, now our denominator still remains the same, plus h plus 2 plus x plus 2 multiplying. Then let us write the division sign in that format, so to avoid double division, double fractions. So we know that this, it is still dividing, the numerator, or this fraction here, the h. Then we're going to say it is equals to, so we know that limit when h approaches 0, the function, we're going to look into the, so I hope you see that x is going to be eliminated by x, and 2 minus 2, and x squared plus x squared minus 2x plus 2x, and minus xh with plus xh. And then we're going to have negative 2h and negative h to give us negative 3h. So always when you do this type of algebraic functions from first principle, the numerator must have at least the term that consists of h, always. And all divided by x plus h plus 2, and then in bracket x plus 2. Let's change the division sign to multiplication. Then 1 goes to the numerator, and then h goes to, it goes to the numerator, h goes to the denominator. Then from there, we're going to start simplifying. We know that in the meantime, I'll advise you start substituting 0 while you're dividing it. So h will divide h. We'll be left with a negative 3. Then all divided by. Please substitute the value of h in the meantime. So we'll have x plus, now is 0, plus 2, in bracket x plus 2. X plus 2. And then, therefore, the final answer will be equals to. So I hope you see that this, we're having x plus 2 times x plus 2. So therefore, the final answer is negative 3, all divided by x plus 2, all in all to the power of 2. That is the solution for question 2.1. Question 2.1. Y is equals to arc cosec. So 2.2, we need to make a neat sketch of graph of arc cosec. Arc cosec x for the range which is 0 is to pi. 0 is to pi. Sorry if it's not that clear. So range is 0 is to pi. So that is the range. This, so when we talk about range, we know these are x values, isn't it? Hmm? It's y values. So range is y values, then domain is our x values. So we have a range then of 0 to pi. Now, in fact, just want to give a tip when you want to draw this type of graphs. So first of all, you need to go back to the reciprocal function of cosec. So reciprocal function of cosec, it's what? It's 1 over. So 1 over sine. Let's say 1 over sine x. So just start there. And now, for an example, if let's say you know the graph of sine, let's start with sine. So you know the graph of what? Of sine. Graph of sine will start at 0, right? And it turns, and let's say complete a cycle at what's that? At 360 degrees. So 0 to pi is similar things. So therefore, when it comes to inverse of or arcsine, so arcsine, what it will do, so arcsine graph. So this is a sine graph. So arcsine graph, what is going to do, let's say this is an arcsine graph for x. So if let's say this was having a horizontal, in fact the amplitude, which let's say reaching, for an example, amplitude a here and amplitude minus a. With an arcsine graph, what it will do, let's say maybe this is now the x axis. So it will do the same thing. It will start in this format. It will do so. It will do something like that. It will fluctuate in that way and complete 360 degrees. That is an arcsine graph. It will do that. So, which is cosec x. So, with the values that I'm getting, let's hope we have the same values y, then this is y value. So x value, if we have 0, and then it says infinity, right? So there's an asymptote there. So there's an asymptote at 0. And at 15, I have 3 point, let me say 8, let's say 86. Let me leave it at 86. Managed to blow. At 15, 3.86. So about that. At 30, what did you get? 2. So at 30, we have 2. At 45, what do you have? 1.41. Yeah. And then at 60, so 1.1, let's say 1.15, it's getting lower. And at 75, what do we have? 1.0. Yeah, let's say 0.4. Ending off. At 90, we have 1. And then it starts dropping back again. It will be duplicating this one. I always put small tables. And then going down. So, as we still continue, let me just write the other one, because I said to a student, I must make sure I show you everything. 90. Okay, we went to 105. Ne? 105, we got 1.04. And then 120, it's 1.15. You see, it looks like this one, 60. So it's like a doubling 60, doubling 45. Way to get that. And 120, 135. 135 is 1.41. And at 150, so it's 2. And 165, 3.86. Or at least final 180. So there's an asymptote. There's an asymptote. Okay, so but sorry to go this longer route, but I wanted you to know how cosec graph is going to look like. Cosec graph. So inverse of that, we know it flips. It flips. So let's say we have your cosec graph there. Let me try 180. But normally we are used to, let's say 0. So I wanted to see, will it fit? Please allow me to put 30. and let's say 45, the ones that we're used to, and 60, and the other one that we're used to, uh, it jumps, we went to 90, and 120. Yeah, and I'm stepping by that. So I wanted you to see your, what do you call, how your graph is going to look like. So the values that we got, all of them, they're positive. It means that the y you're going to plot upwards. So let's just go and check. Let's say it's 0. At 0, it says what? Undefined, right? It means that at 0, you're having what? A vertical asymptote. The function is not going to pass through there. So it means that it will be diverging in that direction. Number 2, let's go and look at, we can try and look at 15. At 15, I hope you saw. Let me just put 1, 2, 3. So 1, 2, 3. So at 3, we had 3.86, isn't it? Let me zoom it somewhere there. At 15. Ta 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 ta. I have a point there. And then at 30, what do we have? We have 2. We have a point there. And at 45, it's 1.4, right? I'll zoom it somewhere there. Halfway, so 1.4. Now at 60, it's 1.15, right? So it's approximately 1, but 1.15, somewhere there. Then at 75, right? At 75, again, 1 point, it's 1.04, 1.04. Then at 90, what do we have? So it's exactly 1. At 90, exactly 1. But at 120, I hope you see it start going where? At 1.04. 1.04 at 120. So which means we are there. And it's 1.15. Let me just take it to 1.15. But I skipped this one here, 105. Then let's just look at 150. At 150, it's approximately somewhere there. Let me drag 2. 2 is there. And can we even involve 165? Let's involve 165 so you can see. So 165 is 3.8. We have 3.8. And then at 180, it says what? Error, isn't it? It means the graph is not going to pass through 180. There's a vertical asymptote. So asymptote for that graph, it is the 0 and what? The 180 degrees. So you can just join those points and curve it at 90 and then have it there. But what will happen, it will continue to infinity, diverging through 180 and through the x-axis. So it will diverge to to infinity. If let's say we're given, let's say, what is it? Domain values. This other side, it was gonna flip and it was gonna bend downwards on the negative side. But again, using the values of negative x and negative y. And negative y. So that is a cosec graph. So I wanted to show you that don't waste your time. If you're smart, use your calculator. If you have 1 over sine, it is cosec. And have those values accordingly. But now we are talking about arc cosec. Arc cosec. So we're talking about arc cosec. So what the okay, I was gonna plot in the same graph, but let me do this. But with arc cosec, they switch values. These values of x will be values of y. The values of x will be values of y. So we are going to, when you are going to plot arc cosec, please just do this in your calculator and have the values. When you are going to plot, I will advise you to be smart in your calculator. You will assume that, oh, these are x values, these are y values. So when you plot, you do the table, just do the table quickly. When you have utilized your calculator, do the table quickly and say, oh, the values that I said were x values are going to be y values. You just change them and say y. The other ones are x. So I have this is 0, this is 15, and you mention this is 30, 45, and 60, and so on. But using the same table. Here we said these are x values, but now they are y values. It's an arc cosec. So this is 4 arc of cosec. So that arc cosec x. So it opposes the graph of cosec function. So when we are going to plot arc cosec, the arc cosec graph, it's going to be now your y-axis is carrying the degrees. It's going to carry the degrees. So what happens? We know that here we started at 0 and 30. Let me use 30 and 60 and 90, 120, 150, 180. We know at 0 and 180 we have asymptote. So it opposes, if at 180 you had a vertical asymptote, this is going to be a horizontal asymptote, 180 degrees. Though they didn't say 180 were given as pi, but we know that in degrees, this is radians in degrees, we have 180 degrees. Here we said 45, no? Said 60. Here we said 90, 120, 150 degrees. So that will be your range. And then the domain values is the ones that we got. I remember we had 1, 2, and 3. So when you plot your graph, we know this is 1, this is 2, this is 3. So we said that if y is 0, then the function diverges to infinity. At 15, when y is 15 degrees, let me skip 15. At 30, what did we have? It was 2, right? At 30, we had what? We had 2. Though at 15, we had 3 point something, or somewhere here. But at 60, what do we have? 1.15, somewhere. And at 90, it goes to 1. So again, this points here, they will be mirrored on the other side because it's turning at 90. Then at 120, we had, it's 1.15. Eh? I lost the table. So at 120, it's 1.15, right? You'll agree with me? And at 150, we know it's 2, isn't it? So at 150 is 2. So the arc cosec graph, if you chose to step by 30, you'll be having that. So this is y equals to arc cosec x. So that is an arc cosec x when the range was given as 0 to pi. We're not given from negative pi to positive pi. So I hope now you see how we plot an arc cosec graph. So I wanted to re-explain that because I know you haven't plotted graphs of arc inverse trigonometric functions. The key thing, please make sure know the normal graph. Let's say if it was sine, for an example, know the sine graph, but an arc sine, you know that you're going to switch the values of y and x. You just switch the values if you have done the table. Bending upwards, bending to the right. Okay, I hope we're done with 2.2. Though it doesn't weigh a lot of marks, it's a few marks, but I think it's even 2 marks. So, but it's because I was explaining that you understand. It's explaining that you understand. Okay, with all the graph, the sec, cosec, arc, chord, stick to the main ones that you know. You know the reciprocal functions. Just deal with the reciprocal function. Use these when you punch in the calculator. Table method works very well. Calculator file. You're done. 5 minutes, you plot. But because with me, for an example, I know for cosec graph, it will go in this way, then I'm going to bend it upwards. For sine graph, I know it ends where. Then if I flip, I was going to flip accordingly. And dy over dx of each of the following cases. We're given y, it is equals to, okay, this is a change of functions. Y equals to, in bracket, ln x squared plus 1 minus arctan 3x, those bracket, and all in all to the power of 6. To the power of 6. So we're given y equals to ln x squared plus 1 minus arctan 3x to the power of 6. So it's question 3.1, your 2018 question paper. And you said it was when? It is in July. It was July, it was T2. Some professor, you never know when the type of paper can come this block. I have that instinct most of the time. And someone can say, maybe I'm the one who set the paper and the main exam. I'm talking about main exam. Okay, so let's do inspection now here. We have the main thing, the key, it is we see an exponent there. That is a change of functions. It means we have to start applying chain rule. We need to apply chain rule. That is the first step we have to do. Now, the second part, we inspect inside. It means we're going to derivate using natural logarithm and using inverse trigonometric functions. Inverse trigonometric functions. So, we start, everything is in standard form. Therefore, looking for dy over dx is equals to derivative of y is dy over dx. Now, according to change of functions, we are going to multiply the bracket by the exponent, and therefore ln x squared plus 1 minus arctan 1 arctan 3x. All in all, now subtract 1 from the exponent, which is going to be 5. Therefore, we need to multiply now by the derivative of the functions inside the bracket. So we know we start, at least this is a difference of two functions, it's not product. So we're going to start, we derivate ln x squared. It's going to be 1 over x squared plus 1. So 1 over the function inside the ln. Now in the numerator, we know that we must multiply by the derivative of x squared plus 1. So what is derivative of x squared plus 1? So it is going to be 2x. We're supposed to replace this by e, but ln e is equals to 1. So therefore, derivative of ln x is 2x over x squared plus 1. Therefore, minus. Then what is the derivative of arctan 3x? We know it's the same thing. The formula states that it must be the derivative in the numerator, and we must is it a square or is not? The arctan. So it must be 1 minus of x squared. 1 plus f of x all squared. I lost my formula sheet here. So according to derivative of trigonometric functions, So we have 1 plus x squared, right? So, but we know it is going to be 1 plus the function inside what? The trigonometric function. So it is going to be 3x all in all to the power of what? The power of 2. Then the rule says that in the numerator we must have the derivative of the function inside the tan there. So derivative of 3x is 3, isn't it? That is the rule. But if it was just x, derivative was going to be 1, then all divided by 1 plus the x squared there. So now it is d squared, then the numerator must have the derivative of the trigonometric functions. Check the formula sheet. Let me pause. Check the formula sheet, arctan. Don't check the arctan x. Check the arctan f. Or if you want to add fractions, you can even add fractions, but it's not necessary. It's not necessary. So that's why it was 3 marks. The chains of functions, derivative of ln, derivative of arctan. So 1 mark. So if this is derivated accordingly, what is that? If that was derivated accordingly, you can mark that a mark, and that will be a mark.